Hi, welcome back to another episode of Introduction to Computer Networks. This is Polly again. And yeah, let's go ahead and check on what we need to do this week. So this is week 11, episode 20. And the assignments this week will be very straightforward, just 2 of them, and both of them are just for you to exercise. I guess the reason having a really light load this week is because exam 2 is coming up tomorrow. Okay, based on how you guys did for exam 1, I think exam 2 is not gonna be too much of trouble. But I have to say that I've tuned up the difficulty a level. Okay, given observing how you guys did in exam 1. But guys, what I want to say is simply that whatever you do, whatever the outcome is, it is you. You can be proud of. Sometimes I feel like the life is a constraint satisfaction problem. So we all have all kinds of constraints that we need to satisfy. And it has a lot to do with the objectives we set early on. And I understand that things can get complicated when you kind of underestimate the constraint rise from a certain objective. Okay, so Polly has also one constraint to satisfy next week, which is here. So I'll be on conference travel next week. And I'll be travel to some place that's far. So what I would do is to try to stream from the remote location. But I'm still not sure whether the connectivity is going to be stable enough to warrant a steady stream, to warrant steady lecture. Okay, so in case that's not possible, Polly will post the videos to watch and the quizzes to work on to cover the week of work. All right. So yeah, I guess this is week 11. We have just 5 weeks left. As I said, we've already set the objectives. The constraints are already there, even though that we are all loaded. But let's try to keep going, hanging there, and see if we could get the semester through. All right. And I see that, hey, many of you are resilient, right? You guys are still joining the streaming sessions. For some reason, this semester is not exactly easy for me because of all the commitments Polly has said early on before the semester starts. But you see, yeah, that's, hanging there and try to get things done. So, 佑成、博元, Jordan, 一心, 博宇, and 新闻. Okay, yeah, that's keep going. All right. And the first topic today is actually to wrap up TCP. By now, you've known very well how TCP works. There's just a little bit remaining. This is ECN explicit condition control that's already embedded in TCP but rarely used. Okay, and this is the part of TCP that implements a network assisted approach. Okay, and this is the part of TCP that requires support from the network layer, and that is actually not deployed widespread, and this is also why TCP's ECN option is very often deactivated. Okay, so this video, 3.5 minutes, explains if it's activated, how it worked. That was TCP, taking the end-to-end approach. Let me introduce another mechanism that's called the ECN. It's also defined for TCP/IP for the internet, but it's not really implemented or activated. And it's taking the opposite approach, the network-assisted approach. The ECN mechanism works this way. First of all, in the IP packet header, okay, or network layer header, there's this special field called TOS that stands for type of service. So in that field, 2 of the bits are assigned for the purpose. They are also called the ECN bits. Okay. I'm using a green packet here to indicate that that packet header, especially the network layer header, is carrying the ECN bits. They were initialized to 0, that means no congestion, but as the packet travels through the network, running into a busy router like this, the bits will be turned on. And the packet will eventually come, okay, and arrive at the receiver of the data. And the network layer here at the receiver is going to see, oh, these 2 bits are turned on, therefore notifying the transport layer. And at that point, okay, the transport layer of the receiver is going to do this. Receiver is going to set the ECE bit on the packet, going back to the data source, like this. Okay, so it's going to be in the ACK packet, and the ECE bit being turned on. So this is also called the E flag, okay, in the TCP packet field. Sender there, upon receiving this ECE bit packet, will then send a packet that is then the data packet going back to the receiver. And that packet is a little bit special because there's also a special bit being turned on, the CWR bit. So this is congestion window reduced bit. This is so that the destination here, the receiver of the data here knows that, okay, so my notification here, you indeed received it and reduced the sending rate. Okay, so therefore the receiver of the data does not need to send ECE bit again. Okay, otherwise, the source is going to reduce sending rate again and again. Right? And the E bit and the C bit, the E flag and the C flag are in fact, again, in the TCP packet header. Okay, so along with all these other flags for TCP. And that finally takes us to the summary of the chapter 3. We went through the basic functionalities of transport layer protocols, multiplexing, demultiplexing, reliable data transfer, flow control, and just now, congestion control. And we talk about how UDP and TCP implement these services. Particularly, we spend quite a lot of time here, as well as here. We are now finally ready to leave the network edge. So departing from the transport layer and down to the network layer and into the network core. But the network layer is going to be split into 2 chapters. Chapter 4 is going to be about the data plane, how we forward packets real fast. And chapter 5 is going to be the data plane. So how do we control these paths we select such that the packet will travel and eventually reaching the destination, reaching the receiver. All right, so towards the end of the video, it's not bad to see a summary of chapter 3. That might be useful for tomorrow. But at the very end of the video, you see that chapter 5 and chapter 4 are related. They both, the 2 chapters together explains how the network layer works. All right, and but that is just a very high level overview. Next video here is the official overview. You will see that in the network layer, we'll begin to send data as datagrams, and they will travel from one end through all the routers in the middle until it reach the other end. Okay, and mostly in this video, you will hear that there are 2 major functions in the network layer. So this video a little bit long, 5.5 minutes. Welcome to chapter 4, the network layer, and particularly the data plane. So in this chapter, the goals are understanding the principles behind these network layer protocols. And we'll focus on data plane and talk about the other one, the control plane, in chapter 5. So in the overview section, we're going to talk about the service models possible for these network layer services. And we'll talk about the main functionalities that people implement in the network layer. Forwarding and routing. We'll talk more about these. And we'll be spending some time here talking about the architecture of a router and how packets travel through a router. And the rest of the chapter will be spending a lot more time here talking about forwarding of packets generally, as well as how it's implemented, how it's working on the internet. 4.1, the overview of network layer. Well, what the network layer is doing is simply this: transport segments from the sending host to the receiving host. So let's use the micro internet here as an example. And let's assume this guy here is the sending host, and this guy here is the receiving host. So the goal of the network layer service is so that we could send segments or packets through the internet to the receiving host. Now, What's a bit special though, okay, in the network layer? It's not only the two end hosts have the network layer protocol implemented and operating on the machine. Each and every router inside the network here would also have the network layer protocols running. Now to be exact, okay, on the sending side, on the sending host here, the transport layer segments is going to be encapsulated into the datagrams. So a packet at the transport layer is called the segment. But when a packet now goes into the network layer, it's called a datagram. And sometimes also called the IP datagram. Okay, so transport layer, TCP layer. Network layer, IP layer. Transport layer, we have the TCP segments. Network layer, we have the IP datagrams. Okay, so at the sending side, we encapsulate these transport layer segments into the IP datagrams. Now these grams, okay, datagrams will go on to the network and travel from router to router. And each of the router will examine something special, okay, in the packet header, in the IP datagram header, okay, and decide where to pass it further on. So that magic we'll talk about more in the sections to come. Finally, when the packet arrives at the receiving side, okay, so this is the receiving host, yeah, the network layer is going to look at the datagram, remove the packet header, and pass the segment, okay, up to the transport layer. So that is the lifetime of a packet traveling the network through the network layer. So in anime, so packet coming from above, pending the header, so packet gets a bit bigger, and you see routers busy forwarding the packet and eventually reaching the receiving host. And at the network layer header or the IP datagram header removed and the segment restored and pushed up, okay, to the higher layer. All right, so that is the general picture of what the network layer protocol is doing. Now, the network layer protocol is doing two major functionalities. As you observed earlier, yes, forwarding. The routers are all busy moving packets around from one router to another router. Hopefully, it gets to the next router that is appropriate so we don't take too much time to pass the packets until it reaches the receiving host. The other is this, okay, this is also the magic that I was talking about. So this is the computation, the intelligence in the network layer that determines, okay, a route between a pair of sending host and the receiving host. Or a lot of times we just call them the source and the destinations. So to determine an end-to-end path to travel over the internet from the source to the destination. And that intelligence is also called the routing algorithms. An analogy is this. Let's assume the class is taking a trip to Canteen. Yeah, I know the weather is getting warm. It would be really nice if we're in Canteen. Okay. Well, the thing you need to do first is this, routing. You pre-compute or you Google, okay, and come up with a plan, okay, for the day of travel. Whether we take a bus to the Taipei station or we take a metro to the Taipei station. And from the Taipei station, do we take a high-speed rail? And from the high-speed rail station at Kaohsiung, do we take another bus or do we all rent a car or rent a number of these bikes so that we ride along all the way to Canteen? Okay, so the computation process, the intelligence that we need to do ahead of the travel is called the routing. Now, on the day of travel, we'll bring this Google map printout saying, hey, you start from home, you walk to a particular station, and you hop on a particular metro line. And once you get to the Taipei station, you just hop onto, high-speed rail number 112. And then after arriving at Kaohsiung, you go to a particular bus stop, and then you hop on the next vehicle taking you to Canteen. So that is this forwarding. Okay, so at every interchange point, you look up a piece of paper and find out what is the next step to do. So this way, it ensures that the forwarding part, the traveling part is going to be fast and smooth. So the separation or the differentiation between the routing function and the forwarding function. All right, so next is data plane and control plane, an extended overview. So in this video, we'll talk about how the control plane at the top, data plane at the bottom interact, and how we did things in the traditional way, and how we changed the way we send data over the internet. So there's a more modern way, okay, to adapt to the need of certain areas of the internet. So that new way of doing forwarding routing might not be extended to the entire internet. So it's a mix of a traditional way and the modern way of doing routing and forwarding. So this video, very important in fact. It's not hard, but very important.
And that should make it a bit clear for you to see the separation between data plane and the control plane. So by data plane, we actually meant to talk about the forwarding function. Okay? And the control plane, on the other hand, is the routing function, the part that is trying to identify a path between the source and the destination. Now let's talk a bit more about the data plane. Okay, so what's being done there is very local. Each router is determining for each incoming datagram who should be the next router to forward it further. Okay? And that is the forwarding function. So it's illustrated here. For a datagram coming in, this router here is looking up a table and find out, oh, this should be the outgoing port and therefore reaching the next router. Now, the control plane, on the other hand, is the part implementing the routing functionality, okay, implementing the intelligence. It is to determine, okay, how would the packets be able to travel end to end from the source to the destination. So these routing algorithms will be implemented in the control plane. Now there are two different approaches implementing the control plane. One is the traditional approach. The other is called the SDN approach. Okay? The traditional one is the distributed approach. And the modern one, the SDN one, is actually more centralized. Okay? To your surprise, isn't it? Okay, we are actually moving from distributed solution to centralized solution. Now in the traditional one, each router will be implementing the routing algorithm, and the routers will also exchange information among themselves. As a result, and collaboratively, they calculate an end-to-end path. Now, in this centralized approach, in the SDN, we actually ask a couple very powerful machines, okay, a couple very powerful SDN servers that are actually sitting far away from the routers to do the computation. And then after the computation is done, they're gonna install the routes back into the routers. Okay? So the tables are actually computed on the routers locally in the traditional way. But more recently, the modern way is to have some powerful machines computing all the routes and then install them back to the local routers. And local routers no longer do the complex route computation. So let's talk a bit more about the data plane. So this is the forwarding part. So this is the part implementing the per router action. Okay? And it's very simple, very fast. Okay? All that is done is the packet coming in. The router look at the specific packet header field and match to an entry in the forwarding table. Okay? So this is called the fast output interface lookup. Okay? Once we get a match, we get also the outgoing interface. Okay? Let me illustrate. So these are the routers. Okay? And inside the router, okay, you see this is the entire operating system stack. Okay? There's this thing called the forwarding table, and each router will have one of these. Okay? When there's a packet coming in like this, it's going to look into a packet header field and matching the pattern here to the entries in the table. Now, we see that this guy is the matching entry. Therefore, immediately we see the packet should go out on interface 2. So output interface 2. So this is the direction to forward the packet further, and therefore next is going to arrive here in this router. Okay. So this is exactly the detailed step of packet forwarding in the data plane. And the control plane is here, higher up in the operating system stack. To be more exact, and let's talk about the traditional approach first, where the computation is distributed. So the routing algorithm is going to be running on each of these routers, and up here. The routing algorithm here, 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 and here. So each and every router is going to have the routing algorithms running, and they're going to interact with each other. So there are these exchanges of messages between these routing algorithms distributed on the routers. And this is the control plane. As a result of the computation and exchange, they find out what should be the forwarding table for different incoming packet, for different packets going to different destinations, and install the local forwarding table into the data plane. So this is the separation of the control and the data plane. Now, in the modern days, we take the centralized approach, the SDN approach. Now, it looks a little bit different, the separation of the data and control plane. So routers protocol stack stop right here, because the computation is all where? up here, okay, a couple machines, powerful machines, okay, doing the computation. But it cannot be computing without information provided by the routers here. So these routers, okay, will have a tiny little process running here. They're called the control agent. The control agent here is gonna provide input to the remote controller. This is the big process implementing the routing algorithm. So after collecting information about, hey, who they are and the connectivity of these routers to other neighboring routers, now this controller here can then do the powerful computation. Once the result is obtained, okay, those tables are communicated back, sent back to the control agent, and therefore installed into the data plane of the routers.
Yeah, so you probably see a little bit that with SDN, then you can try to optimize the routes within a certain region. Yeah, that is the purpose of the modern way, which is a little more centralized. Okay, centralized system is not good or not bad. It is just that when you want to have more control, centralized system works better. All right, now we move on to the next topic. It's called L3 service models. So here we have two videos. So what Polly will be talking about is thinking of the network layer as general. So what we have introduced earlier are how internet runs the network layer. Okay, so there's control plane running routing function. There's data plane running the forwarding function. But here we want to talk a bit more generally about the network layer design of general communication networks, okay, not just internet, all right? So the first video talks about that there are actually two models, okay, possible to design a network layer generally, okay, for someone who is devising a new network. Okay, so this video, 3.5 minutes, so you get a rough idea. Oh, actually close to 4 minutes, so you get a rough idea how to design the network layer generally.
Before we talk about the service models implemented at the network layer, let me remind you this. If you recall, when we were talking about RDT, we say sending process, receiving process. If the underlying channel is reliable, all they need to do is just to pass data out and the data is just going to arrive. But unfortunately, yeah, the channel is not exactly reliable. Okay? And depending on how unreliable the channel is, the complexity, okay, of the reliable data transfer service is going to be different. More unreliable, more complex. Less unreliable, less complex. Okay? So the service model we'll be talking about next is to talk about how we implement. Okay? What kind of channel we're providing here. Are we going to provide a more reliable channel or less reliable channel? So more reliable channel is one service model. Less reliable channel is one service model as well. And we could actually have a spectrum of different service models here. There are two major camps of service models. First is the connectionless service. What it meant there is that the end hosts and the routers in the middle, they do not set up any connection-specific states before data being passed around. So there's no reservation of bandwidth, no reservation of memory space to buffer packets. Okay, so you see that there's not going to be any guarantee at all. Exactly. So this connectionless service is also called the best effort model. Okay, and this is exactly the model implemented in TCP/IP, the internet. The second camp, the connection-oriented service, which is the opposite. So the end systems, as well as the routers in the middle, they would actually exchange message and establish a connection before the data flows. Okay. So this is actually implemented in some of the old architectures, old systems. ATM, this is not the bank ATM machine, banking machine that you withdraw money. So this is actually a specific computer network that have been designed in the 20th century. At some point, okay, ATM is actually competing with the internet. I think towards late 90s, okay, still before the turn of 21st century, ATM gets merged into the internet. So some of these routers in the internet, the lower architecture design is actually from ATM. Now, frame relay X25, these are just too old, okay, but these are examples of connection-oriented network layer service. Okay. Now, to establish such a connection will involve routers, okay, and the involvement is actually quite deep. It's complicated enough. It's the third important function, okay, in these systems, on top of routing and forwarding. Okay. Now, one last bit I want to talk about is this. We've heard about connection-oriented service as well when we were talking about TCP, right? TCP, they're sending sing ACK, and then ACK for the sing ACK. Hey, that's establishing connection, right? It sounded very much like these, ATM frame relay X25 is doing. Yes. At the transport layer, TCP is actually establishing connection between two processes. At the network layer, in ATM frame relay X25, they are actually also establishing connections between two hosts. All right? But be careful. Internet at the network layer does not implement connection-oriented service. However, at the transport layer, implements connection-oriented service. So just be clear. Internet, the subject we're talking about and we'll continue to talk about, does implement connection-oriented service at the transport layer, but not at the network layer. Internet, in fact, when it is designed, it does have this complexity at the edge mindset so that we don't do complex things in the network layer involving the routers.
All right, so now you see, in the network layer, one can actually do it connectionless or connection-oriented. And Internet chooses to implement the connectionless model, which is packet switching. And those that you heard earlier in the video, ATM X25, those chose to implement the connection-oriented way, which is circuit switching way. All right, now it connects all the way back to chapter 1 that we talk about how the core of a network can be designed differently. All right. Now the second video is to speak further about these connection-oriented designs. So there could be fine granularities of services they provide. Unlike the Internet one, connectionless, which is very, very primitive. Therefore, at the edge, end-to-end services, end-to-end processes, more work needs to be done. For example, TCP handling such that there's no loss, no error. So the second video, 3 minutes.
Yeah, those are the major CAMs. But within each CAM, you can probably define finer service models so that you provide different levels of service. So for example, we could actually come up with services for individual datagrams, such as guaranteeing the delivery of a particular packet, guaranteeing the delivery of a particular packet within 40 milliseconds. We could also try to provide services guaranteeing the flow of a number of packets. So we ensure that these packets will arrive in order, or we guarantee a certain bandwidth, or we restrict the time differences in between these packets when they arrive. So again, the service models, they can be finer or coarser. It's more like a spectrum. Now what I'm listing here are the 5 services models that have been implemented and being used, at least for some time in ATM's case, and continue to be used today on the internet as well. So the internet service is, the best ever. So essentially, it's not guaranteeing anything, no guarantee at all, and it's not giving condition feedback from the network layer. It's in fact being inferred from the transport layer, between the TCP sender and receiver. Now ATM, quite sophisticated, provides actually a spectrum of service models. The CBR stands for constant bit rate service. So it actually guarantees a constant rate. So this is perfect for the constant data streams. It guarantees such that there's no loss, packet arriving in order, and the timing of the packets is also guaranteed. It's going to be constant. And there's not going to be congestion at all, so there's no need of congestion feedback. Variable bit rate service. So this is actually guaranteeing the maximum bandwidth required by a variable bit rate data stream. So there's no loss because we are guaranteeing to the maximum rate, right? So packet arriving in order, there's no delay as well, no congestion. So you see here, these two are highly guaranteeing everything, but one for the constant data stream, this one is for the variable rate data stream. Now these two, however, available bit rate service. So this is only guarantee a minimum rate. Therefore, there could be losses and the timing cannot be guaranteed because there's a lower rate. Packet could arrive faster than they can go out. So they could get buffer, they could get dropped at the buffer. But in ATM, even though there's no guarantee of the bandwidth delay, but there will be explicit congestion signal back to the data source. And UBR, on the other hand, in ATM, so this is the minimum level of service in ATM. It's called the unspecified bitrate service. So there's no guarantee of bandwidth, no loss. Packet will still be arriving in order. That's special about ATM because it's, after all, still a circuit switch network. And there's no timing guarantee. And in this case, no longer a congestion signal going back to the data source. So you see, again, network layer service model, it can be a full spectrum. Just that unfortunately in internet, or fortunately in internet, there's just one model we talk about, the best ever.
I don't know if you find the best ever service internet provides at the network layer is fortunate or not. Okay, Polly would rather think that it's fortunate. Because one can always try to address the issues at the end. It's just that the performance might not be optimum all the time, right? Now we move on to a very important topic. This is the first time you will see the architecture of a router. So you will see where the routing function is and where the forwarding switching function is running and where the forwarding and lookup process is running. Okay, so towards the end of the video, you will see that there's this very special component called the input interfaces. Okay, that's where forwarding is done. The packet destination address lookup is done. So this video, a little bit long, 5 minutes.
Now let's take a look into the inside of a router. This is the general architecture. We do have a processor, which is doing the routing algorithm. So the complex route computation is being done here. The processor is quite high-end, very much comparable to the CPU, high-end CPUs we're using these days, except that the processor here might be a bit more optimized for route computation. Second most important entity, the switching fabric. Well, people will argue this is probably the most important entity because this is the part of the router that is doing the actual switching, the actual moving of the packets. Okay? And we know that the packet needs to be moved very, very fast. So these switching fabrics definitely needs to be high speed. Third, the input and output ports. Okay, by output ports, input ports, I actually meant that these network interface cards, okay, that we use to connect to the routers that are, passing data in, passing packets in, as well as connecting to routers, okay, that we pass the packets out. Okay. Now, you see then, yeah, the lower part is where the packets are flowing through. So this is the data plane, meaning this is the part of the router that we are flowing the data. So the functionality there, very important, just to move packets. In order to be very, very fast, yeah, the computation, the switching there is pretty much hardware optimized. And so they can work in this time scale, the nano time scale. On the other hand, the upper plane, that is the control plane. Now we have the routing algorithm implemented as software running there. So in addition to routing, it does also a little bit of the management of the router. Okay, for example, tracking, monitoring, how many packets coming in, how many packets going out, things like that. Okay. Now, this part being implemented in software then operates in a slower time scale, the millisecond time scale. Now, the one most important functionality for the router to do is forwarding. Now, it also does route computation here. Now, connection between the route computation and the forwarding here is this. After the route is computed, we install the forwarding table into the memory of the incoming network interface here. Let's zoom in a little bit more into the input network interface so that we see a little bit more the forwarding functionality. Where does it happen? And it's happening right here. Okay, the component that's connecting the input network interface to the switching fabric. Okay. So what's being done there is essentially switching, and it's done in a decentralized way, meaning for each of these input port, each of these input network interface, there's a lookup processor. Okay. So the forwarding of packets coming into each of these input port is done parallel across all these input ports. So that's what they meant here, decentralized. So each lookup processor here is doing this. It looks into the header fields in the packet, okay? And it's seeking the output port using a forwarding table that's installed from the route processor, and that is installed already into the input port memory here, okay, right here. The goal here for the incoming network interface is so that it can complete the input port processing, the lookup forwarding at the line speed. Meaning, if this is the speed of packets coming in, now this forwarding process needs to be fast enough so that we get the same output speed here. If this is slow and this is fast, so if this is R prime and R prime is smaller than R, then we'll end up having this. Packet gets queued. Packets need to wait somewhere in a temporary buffer before they can go out. So that's queuing. Datagrams, if they arrive faster than going out into the switch fabric, then there's queuing delay. Now, there are two different kinds of forwarding. In the traditional internet, we do the destination-based forwarding, which is to look at the packet header fields, particularly the destination IP address, and only the destination IP address. Now, in SDN, the modern routing, it's called the generalized forwarding because we can actually look at multiple header field values, not just one. And it can be arbitrary combination of these header fields. So it's a lot more general. But you can also see that provided the same lookup processor, this is going to be a bit faster and this is going to be a bit slower. So in order to keep up the speed, if the incoming is R and output is R prime here, in order to make sure this R prime is as high as possible, usually in SDN, these SDN routers will need a faster lookup processor here. So this one here, SDN routers, more expensive, while this one here, usually more affordable.
All right, now let's talk about the destination-based forwarding first. Later on we'll talk about the more general modern forwarding. And the traditional destination address-based forwarding is using this technique called the longest prefix. And there are many good reasons doing the longest prefix. So pay attention to this video, 5.5 minutes, but right after that, there'll be 2 quizzes coming up, back to back, testing you whether you understand what is longest prefix matching based destination address table lookup.
So that was the router architecture. Now, there's one thing I want to talk about which is very, very relevant to the rest of the chapter. Destination-based forwarding. As you heard, forwarding is based on, for each packet coming in, look at the packet header field and try to match an entry in the forwarding table. So if the destination address says this, 11001000, matching this guy here, then we take this output port, output link interface. If it matches, for example, this IP address, then we take output port 2. What happened inside this forwarding table is, if you think about it, right, there are so many possible destinations on the internet. And for each destination, there needs to be an entry, isn't it? So this particular destination's output interface being 0. So in fact, in a forwarding table, you should be seeing for each possible IP address, what is the output link interface? For each of these IP addresses, what is the output link interface? But the thing is this. How many possible destinations there can be? Well, the IP address is this big. The IP address, 8 bits, 8 bits, 8 bits, 8 bits together, 32 bits. So you could have actually 1 gig entries. And each entry might require, you see, 4 bits, 4 8 bits, that means at least 4 bytes, and maybe another byte here for the link interface. So each entry here at least needs to be 5 bytes. So 5 gig, 5 bytes, and that would be 5 gigabyte at least, just to keep the forwarding table. So the input port network card there, it's going to require not just a high-speed lookup processor, but also a lot of memory space. In addition to the buffer space might be required, right, in case queuing occur. So that particular interface there is already very costly. And if you need to have many input ports, many output ports, think about the cost of a very high-end router, very expensive. And that's not going to scale very well if we actually, expands the IP address space. So this is a 32 bits IP address. This is IP version 4. Later on, you will see. There's another version of the IP layer protocol. That's called the IP version 6. And the address space there is actually expanded to 28. So this approach, each IP, each entry is not going to scale very well. So what's really being done on the internet is this. We do matching, all right, but not match the entire IP address. We only match the prefix, okay, of the IP address. So we're doing table lookup is to do matching, but we are only matching to the longest prefix. Okay. So this is what we do when we're looking up in the forwarding table entry. So given the destination address, okay, so we'll take this address and match the entries here. Okay. This time we don't have one entry per IP address. It's actually an aggregated or the prefix. So what you're seeing here is we only specify the first part of the IP address and leave the rest general. Okay. So that is also saying that as long as the destination address, the first few bytes match this pattern, okay, the rest of the IP address can be general, free. Okay. Now, as long as you have a destination IP address looking like this, then we take this packet to this output port. And the second entry is saying that okay, if the IP address matches this pattern, the rest can be flexible. No matter what, we go to output port 1. Now, there could be multiple entries. For example, this guy here and this guy here, you see here. Oh, up to this point, they are the same. So you could have an IP address matching both entries, isn't it? So in this case, we'll take the longest prefix. Okay, we'll take the entry that the destination IP address matches the longest. Okay, now, in case the rest of the 3-bit of this IP address is 000, then we forward that packet to output 1. If it's something like 101, then it does not quite match this entry. However, matching this entry, then we send it to output 2. All right. So let's exercise a little bit. Now, if we get a packet, the destination address is this. What should be the output interface? Let's see. The first 8 bits match. Great. In fact, all these 3 entries, the first 16 bits, actually 19, 20, yeah, the first 20 bits are all the same. So these two destination address, I think the first 20 bits are also the same. So what differs is beginning from the 21st bits. So which entry in the forwarding table does the first destination address match? Well, this is 0. So only this entry match, right? Because this is 1, this is 1. So these two not matching. Therefore, this packet goes to interface 0. Now, the second destination here. Oh, 21st bit is 1. So it should be either one of these. Now, 0, 0, 0. Well, it actually matches more the second entry. Therefore, the outgoing interface for the second destination address being 1. And that takes us to a double quiz time.
All right, so this is quiz 33, the first one of the double quiz. So, yeah, so what we're doing here is to try to role play a router, okay, particularly the input buffer there, the input interface there, trying to do the longest prefix match. So let's assume that the table is already there. So this is actually established by the routing part, okay, of the router, okay. So that's given. And being the input interface, all you do is just check the destination address in the packet header and then decide which of these 4 interfaces this packet should go. All right? And we have 4 of these packets coming along. Tell which interface for packet 1, packet 2, 3, and 4 should go. And that's very straightforward if you follow the video. So let's go to the Discord space. Quiz 33, I'm sorry. Quiz 33 right here, okay? It's actually in the quiz part 3 now, okay? Guys, we are actually moving on to the third part of the semester. So, guys, you have only 2 minutes, okay? Let's start counting time. So let's see. Okay, this is the same forwarding table we have, right? The first 20 bits, all the same. First 20 bits, the same. All right. First 20 bits, 0, 0, 0, 0, 1. Okay? So this match one of these. And this one obviously not matching of those, therefore we take the otherwise interface. So this should be 3. And then 0, 1. So this one matches, I think, 0. Matches both 1. Oh, and this one 0, 0. So this should be all right, I have here 0, 3, 1, 2, and I see team 18. Wow, all right, very fast. 0, 3, 1, 2, there you go. Same for team 12, team 10. Wow, all right. 0, 3, 1, 2. I guess you guys get things done almost at the same time, right? 204, 204. 204. Okay, bonus to all those that are early enough. All right, so you see, again, Polly was right. This is straightforward. So this is what the input interfaces, the forwarding processors is doing. Okay, longest prefix match to save memory, to also shorten the time, because you only have like 3, 4 entries to look up to, instead of having lots of entries, isn't it? And guys, yeah, you guys did really well. Let's move on to the last one, which is quiz 34. All right, so hey, now we'll role play a little bit the routing part of the router and come up with these longest prefix matching entries, okay, on the forwarding table. So this is like saying, hey, how can you write the prefix for this range of IP addresses and write the prefix for this range of IP addresses? You know, guys, give it a try. It's also not that hard. All right, you have to also 2 minutes. Okay, let's go to the Discord space and move to quiz 24. Good, I see you guys are working on it. That's good sign. Okay, 2 minutes. You will also try to do this. You know what? All the way. Yeah, the range begin to diverge from this bit, right? So it would then be the whole string and then 4 stars. There we go for the first entry. Easy. I think we can take the similar approach, isn't it? Let's check, right? All the way. It begins to diverge from this bit. Therefore, it's this string with many more stars. 6 plus 8, 14 stars from here on, isn't it? So this is the prefix. Last entry, it matches all the way here, right? So here's the prefix. All right, so I think this is also easy enough. All right, yeah. Yeah, guys, not so hard, isn't it? Oh, wow, this is perfect, Andrew. Yeah, so the stars represent free patterns. Okay, so arbitrary. Okay, I take this as answer as well, because in the previous example, right, we see that the routing table actually, the forwarding table writes only to the last bit that matches and leave the rest empty. All right, good. I trust that you guys pick this one up as well. Easy. There you go. Ancient. Oh, having strong support from the teammate. That's really nice of you. 博元. All right, good. So, guys, easy. But what might be a little bit troublesome coming up is exam number 2 tomorrow. All right, so take it this way. What else can you do, right? But just to try the best you can. Okay, so we all have constraints. Whatever outcome, accept it. Okay, whatever the outcome is, accept it. Okay. You might be sad a little bit, but hey, go out, have a good time with friends, play basketball or walk a little bit to let the anxiety out, to let the stress out. That should help. Okay, good. And you know what? That's all the time we have for today, isn't it? So I trust that you guys will all do well. And those students who finish the quiz within a certain time range, you all get the extra credit. All right, and with that said, I say goodbye. See you tomorrow. Okay, bye. Bye. Felix, it's gonna be a little harder. It's gonna be a little harder. No problem. I know you would do well, Felix. You know what? Just being you, then you do well. Just be you, yeah. Okay? All right. And all the best for tomorrow. Three otherwise. Very good. All right, perfect ending. All right, bye.